What else do you want to?
I just wanted to talk about the moon and the stars, and that was pretty much it.
Oh,
But
okay,
so
let's
like
do that.
here, like in the Globe Mall, the moon is lit up by the sun. So like from Earth, you'd see this view here. If the moon's there, both being lit. And so a lot of flat earthers believe the moon is like a light of its own. I would think the moon is not because if you zoom in, this is amateur. This is not a picture from NASA. This is just an amateur astronomer
All right,
just zooming in on the moon. And you can see this is a crater.
all right,
But you see like this dark shadow in the crater?
yeah.
There's a shadow. There's a shadow, a crater with shadows. Do I have that?
How do we see the shadow? How do we see the shadow from this vantage point? Where that
This
means that's sunlight.
Yeah, and so to me that suggests sun is coming in sort of at the angle of my mouse
Hold
is.
on, where's this picture supposedly coming from?
This is just an amateur astronomer. You too
This is
yourself
somebody with a
telescope. Yeah, I found this like online.
so, but the fact you
This
can see
isn't like
shadows, that's
NASA or
interesting
anything
though.
like
Oh
that.
yeah,
No.
no, what can
And
you
so
glean
the
from the?
fact is, and
Yeah.
so that's why I'm thinking like, how can the moon be a light in of itself if there's shadows on it, craters with shadows in them? To me, it makes way more sense to say it's the sun that's lighting it up
Huh.
and
Yeah,
happens to be causing its cycles. Well, here,
certainly.
this
I'm,
is a really cool experiment I saw.
Oh
Like
yeah,
Aristarchus,
okay, of
of
Sanos.
yeah, he
Oh,
estimated
I
this
know. Yeah,
the relative.
no, I don't.
I, he estimated the size of the sun, moon as compared to the Earth's size, and he also estimated the relative distances. This is really cool. So he did have to assume that the moon was being lit up by the sun, but you zoom in, you see craters, it makes sense. So this is a three-quarter moon and a first-quarter moon. If it's being lit up by the sun when it's fully half, you're going to have an angle of 90 degrees here.
Right,
And with that knowledge, you can have an angle. You can start doing trigonometry.
of course.
So if you have two angles of a triangle, you can
You
figure
can
out the third
yeah,
angle.
and you can use parallax and calculate distance.
And using basic trig, you
Well,
can actually figure out the relative distance between us and the moon and us and the sun. Because this small triangle size here, it's you may not know the length of one of the sides, but you can figure out the relative proportion.
hmm,
And so if you measure, you just take to do the math, you just take the
yeah, yeah,
secant of whatever degree here. So if you have 67 degrees between object A and object B, you can figure out the relative distances. So in this one, this is
isn't trig cool?
yeah, it's cool. It's
Yeah,
2.5 times longer this
yeah,
one than this one.
yeah.
It's very simple to calculate. And so then there's this guy, a YouTuber, he calculated it out. So he took one stick, pointed it directly at the moon when it was at three-quarters full, or a
Mhm.
quarter full. And one stick he directed at the sun. And he tried to measure this angle here where my mouse is. And with this angle, he could do the trigonometry to calculate it out. And so he did it on like 3 days. He got 88.3 on one day, 87.5 on one day, and 86.1 on another. So this sort of range he was getting around. Not
So
a
he's
little bit off.
averaging.
So he just took an average there.
Yeah.
And so calculating the math, he was pretty similar to Aristarchus. He got 21 times longer the sun. So by his calculations. Now, modern astronomers, or more precise calculations, they calculate out to about 89.85. So he wasn't actually perfect. And so here you have your flat Earth model. You have someone looking at the moon, and then there's the sun over here. Okay, that's around the low 80s if the flat Earth model were to work.
Mm-hmm.
But with his angle, you're going to have something that looks like this if you have a relative triangle size of 87.3 degrees. The sun would have to be way out here, and the moon would have to be there for this to work.
Right. Wow.
It doesn't work as a model.
Yeah. No, you see that now.
I guess like the flat earther would have to say the moon is not being lit by the sun, even though you can see craters on it with shadows, which is to me it's just kind of strange. So that's how I think they would try and deal with this, but I just
Well,
don't find that
I've
very
seen
compelling.
pictures of the moon though, where it's interesting. Like,
And so like they're able to know the diameter of the Earth,
yeah.
calculate the distance to the moon, and from this math you can. That's how they're actually able to calculate how
But you
far the
see,
sun
but
is
maybe they're
away.
doing this because they're going in. The moon won't give its light, so they're trying to interpret biblical stuff,
Hmm.
and then trying to look for an explanation where that maybe they would think that the flat Earth model
Yeah.
helps that. and that's where they were coming at this from. Whereas people who come at this more from like a
Yeah.
uh,
Yeah.
scientific.
And Aristarchus, he was able to calculate the distance to the moon by using an eclipse. So he knew like the size of the shadow of the Earth by calculating the curve you would see on, like, say, the moon, because you see that dark shadow.
Right.
You could then figure out the size of the Earth's shadow. If you knew all the relative distances, which he calculated with the other experiment, and he knew the size of the Earth from Eratosthenes' calculation, he was able to calculate the relative sizes of the Sun, Moon, and Earth.
Brilliant.
And I just think that's so cool that someone in the ancient world could have done that.
Well, but that's a bias that we have.
Mm-hmm. Yeah.
I want to go back to that ancient world because clearly they knew far more than we knew. Like, well, you're interacting with.
Yeah. Well, it shows that they are really intelligent. Like they don't have a lot to work with, but what they're working with, they're getting somewhere. And this is just like a bit of a list of.
What's
this may of the math used, the basic trig he was using. I got from Wikipedia, but like. It's unlikely to use these exact formulations, yet they're a good approximation.
Can you explain any of this?
So, like, basically, it's just how he's calculating the relative distances. So he knows S, L here, and so he just uses similar triangles. So S minus T versus with an S base.
Right.
That's a triangle there. That's going to be a similar triangle to T minus D with an L base.
And
the reasoning that you should be able to do this makes complete sense to me. So here, when we look at this distance, we always see the same face of the moon, because the moon is just so far away when we calculate it out. This is because the moon is tidally locked in its orbit with us.
Okay.
So, as it goes around and around.
So it's 30 times the size of the Earth as the distance of the moon?
Yeah, so the moon is 30 Earths away from us.
Isn't that interesting?
That's about approximately.
Well, hold on. Is there any of those numbers that would make more sense?
I'm not sure if it's exact. That's just an approximation to give you a side. This is the scale we're actually looking at.
Yeah.
Because some people, they just show the moon and the Earth like together, and it's like. But here's the thing: in a flat Earth model, you're going to have it about. We know the sun in the flat Earth model must be around 3,000 miles away.
Right.
So if somebody in the northern hemisphere and the southern hemisphere, they should see different sides of the moon. See, someone down here in like South America, they should see this face of the moon.
Right.
Red.
Oh yeah, perfect. Okay.
Yeah. And someone in the northern hemisphere, they should see the northern. Two different faces.
But they don't.
And also, if the moon is lit up on one side and dark on the other, you're going to see different phases as well.
Right.
Everybody sees this. I don't know if this is a NASA picture, but like...
Everybody basically sees that.
This is what you basically see. Yeah, you should be able to see this.
Well, no, someone was talking about the craters being all very good circles. Like, you could find perfect circles. Like, that looks like almost like a perfect circle right there.
Well, my point is,
on the
why
moon.
is it that everybody...
That's the moon. You're saying that's for sure the
this
moon.
This is a picture. But the point is, you can go outside, you can look at this yourself. You don't have to trust me. You don't have to trust NASA. All you do is just go outside, and you'll always see the same face of the moon. It's because the moon's tidally locked to us. How can this be explained on a flat Earth? Because like you're going to be seeing two entirely different faces.
Right.
You know, this is a huge problem, I think, for a flat Earth model. Some flat Earthers have suggested that the moon maybe is like a disc, so it's just like one picture, so that everyone, no matter, sees the same shape. But the problem is, if the moon was a disc, at a different angle, it would start looking like an ellipse. So this is just the same sort of animation. It's just tipped on its end towards us. So the bottom gets tipped away.
Okay.
Well, the top.
Oh, yeah.
And so if the moon was just like a disc or something like that, to show the same face, we would see the moon turning it into like a ellipse shape, depending on where you're in the world. There's really no way I found that they're able to explain this. Do you understand what I'm saying?
Well, because the perspective in the two different parts of the world at the same time should be different if it's a flat Earth model. It doesn't hold.
But anyone out there can go and observe. No, they're
seeing the same thing. You can get on the phone your buddy somewhere else and say, what's it look like to you?
So, you do have to kind of
So you can do that. You could probably even share it online, this video with people and say, this is what I'm seeing.
Mm-hmm. Yeah.
And you could get 2 live feeds of the moon.
Mm-hmm. Yeah.
2 different parts of the world.
Mm-hmm.
And everybody could watch, and you could go, okay, is it the same moon that everyone's looking at?
Yeah, it's really
You'd
hard
have to find 2 people that was clear skies.
Mm-hmm.
I would imagine that's quite possible. So
Mm-hmm.
if that's possible, that's a good proof. What's the explanation as well for you know how like if you look at the North Star and you keep that slow motion photography and then it shows the trace of all the stars going around like this?
Yeah. Yeah, and so you see like it's in the northern we're in the northern hemisphere.
Yeah.
So I've seen the Little Dipper, I've seen the Big Dipper, I've seen Cassiopeia. Cassiopeia. Okay, I've seen those constellations as well.
I think that's Sagittarius, isn't it? Part of Sagittarius.
I don't know. But yeah, and they all rotate around the North Star Polaris. Okay, in the southern hemisphere, you'll see these constellations. This is the Southern Cross.
Yeah, we don't see that.
I've never seen this.
No, we can't see it. So
now
that's a good argument for them. So
yeah,
how
and
is
so
it? But they have no. Their argument is it's just think if it's flat. If it was flat, you just have to go further out.
Well,
they have an explanation for that. That's not.
I'm not sure their explanation is satisfactory. Like here,
why?
like so
because they can see something.
Well, my point is the North Star would be up where my mouse is, and so
well,
you have this guy here.
They can't see the North Star.
Right? This is just a conceptual idea. So like someone in the southern hemisphere,
they don't see the North Star.
They don't see the North Star. They can't see that.
That really sucks.
No, they can't see the North Star.
But they see the.
But they can see down here. They can see different stars. So you can just by determining the shape of the Earth, you can figure out. Oh, there's certain stars we can see. We can back calculate.
Yeah.
So like in a flat Earth model, everything's under the dome, right? Why is it people in the southern hemisphere can't see the North Star? If they're seeing everything under a dome here, why can't they see stars over here? Why do they see stars near the horizon here?
Yes.
This doesn't make sense to me at all.
You're right. It doesn't make sense.
Yeah. And also, there's stars that are associated with the southern hemisphere. People in South America, they look south. They should see a certain set of stars. People in Australia should look south. They should see a different set of stars.
Yeah.
They shouldn't see
the same thing.
They all see, though, in the southern hemisphere, the Southern Cross. It's universal.
Mm-hmm.
Look at these flags. All these flags contain the Southern Cross constellation. So the flag of Australia, this is the Southern Cross. Because
I never knew what that was.
No, that's the Southern Cross constellation.
Yeah.
So it's like, how can Australians and Brazil both see the same stars? It's just not possible in a flat Earth model.
Yeah.
It's not.
Yeah.
And so here, this is Polaris at the center here. And so this is the northern celestial.
Yeah, that's what I was talking about. Career,
Yeah, this is a pair. Now, in the southern hemisphere, you see the exact opposite rotation and around the southern celestial pole axis. How does this work in a flat Earth model?
Oh, I've never seen that. I've only seen the one conception. I only conceived it as one.
They'll show this.
Yeah.
And
the observed motion of stars can only occur if Earth is a sphere and rotates around its axis.
Like in the flat Earth model, things rotating counterclockwise around Polaris, that works, okay? If you're sitting here, you look there, that looks fine. Like, I think flat Earthers are all living in the northern hemisphere. Because, it all contradicts once you go to the southern hemisphere. But you think about it, if you're living here, what would you see the stars moving if they're spinning in a dome? I would suspect you'd see them moving, left to right. You wouldn't see them spinning around a point and a point in the opposite direction. This is what we observe here.
Mm-hmm.
And so I go, this is not possible on a flat Earth.
It's round.
It's spinning in the opposite direction and around there. Yeah.
Round.
And so anyone can go to the southern hemisphere, country night, just go out, look at the stars, and watch the direction they're spinning. And they're spinning around. Yeah, and this is just basically a diagram conceptualizing the North Star.
That's a good job. So
another thing interesting is how certain seasons you can see certain constellations dominate the sky. So Orion will dominate the winter sky. Leo will dominate these are near the equator, these stars. Scorpius this year. That's where they get the idea of certain months associated.
Oh, okay. I didn't know that.
Yeah, I'm not too big into astrology.
No, I don't.
It's not my thing.
I don't want to do it either.
Yeah. No, the thing is the stars that are behind the moon would be different if someone's observing this.
I'm back to round. I wasn't really gone from the round, but I was open to the flat. And now, you nasty guy, you just took my world and you smashed it into a round ball. Okay. But I think you've made some really fantastic arguments.
Yeah.